Hello. Today we're going to talk about Lewis structures, what they are and why we use them. Lewis structures are representations of molecules that show all electrons, bonding electrons and the non-bonding electrons. Usually, or often, we'll show a bonding pair as a line, non-bonding electrons we just show as two dots. I don't know if we've mentioned this, but when a bond is formed, each bond is 2 electrons. So you need to know that. A covalent bond, is made up of 2 electrons. So this is a bonding pair, and these we'll learn are called lone pairs. They're non-bonding pairs. Electrons, like people, don't like to be alone. We draw Lewis structures for 2 reasons. The first reason, and the main reason, is to help us understand the structure of a molecule. Understanding the structure of a molecule, in turn, helps us understand the properties of that molecule and the substance it makes up, which is very important. We're going to get more into properties and how they relate to structure in our next unit. This unit is about figuring out structure. When we draw Lewis structures, we're going to draw the structure so that each atom in the molecule has 8 valence electrons. This is in general, because there are exceptions. One exception is hydrogen and helium. They will be drawn so they only have 2 valence electrons. Now we could just guess and try to throw the electrons down, but there's actually a method that is very helpful, so that's what I'm going to teach you. So the first thing you're going to do, here we have a molecule, phosphorus chloride. Actually, this is phosphorus monochloride would be the correct way to name this. We don't put mono in front of the front, but we do put mono in covalent compounds in front of, as a subscript, in front of the second substance. So this would be phosphorus monochloride. And just to review, we only use these prefixes when we're naming covalent compounds. And we primarily only write Lewis structures for covalent compounds, because ionic substances, if we've talked about, they don't share electrons, they transfer. So the first thing you're going to do is find the sum of the valence electrons of all the atoms in the polyatomic ion or molecule. And we can draw valence Lewis structures for polyatomic ions because they're essentially molecules that are acting as an ion. In this case, wait a minute, what's going on here? This is supposed to be, okay, when I copied this into my video platform, it moved the 3. So this is phosphorus trichloride. I'm going to change this. I'm going to put the 3 here. Scratch this out. It looks weird. So we need to add up all the electrons. Well, phosphorus has 5 valence electrons. You should know that by looking up in the periodic table. You'll see that it's in group 15. Its valence shell will be S2P3, and these tell you it has 5. Chlorine's in the halogen group, so it's going to have 7 valence electrons. And there are 3 chlorines, so that's 3 times 7. So the total valence electrons for phosphorus trichloride will be 26. So that's your first step, finding all the valence electrons. We're not going to worry about, well, if it's a polyatomic ion, we'll do that one separately. Okay, then you'd have to add or subtract the extra electrons to get to the ionic charge. Okay, the next step is to figure out which atom goes in the middle of this molecule. And you're going to pick, to put in the middle, the least electronegative element as long as it isn't hydrogen. Hydrogen will not be in the middle. So if we look at phosphorus and chlorine, which one is the least electronegative? Well, electronegativity increases as you go across. Here's phosphorus, here's chlorine, so phosphorus is the least electronegative. So you're going to put that in the middle. And then you're going to connect phosphorus to the other chlorines, and there were 3 of them, by bonds, by just one bond, a single bond. So we've drawn 3 bonds here, and we're going to keep track of the electrons we're using in the bonds. That's what we're doing down here. So we started, remember, we started with 26 electrons. That's on your notes. These bonds here, each one is 2 electrons. You have to remember a single bond uses 2 electrons. So far we've used up 6 electrons. So I'm going to subtract that from my total. These 3 bonds so far have used up 6 electrons, leaving me with 20 that I have to distribute. And remember, I have to distribute them in a way that each of these atoms looks like it has an octet of valence electrons. Next step, I'm going to distribute electrons so that all the outer atoms have a complete octet. So I'm going to add 6 electrons to each chlorine, because if I add 6 electrons, and this you could call these 6 electrons or 3 lone pairs, because it's 3 pairs, that means, let's count, this chlorine has 2, 4, 6, plus it's sharing these 2, so we get to count that. So it looks like this chlorine now has 8 valence electrons. Same for these. This chlorine, if I added 6, same thing in this one. I'm going to keep track of my electrons, so I've distributed, let's count, 2, 4, 6, 8, 10, 12, 14, 16, 18. I've distributed 18, so I had 20 left from the previous page. Now I've taken away 18, so I just have 2 left. Okay, I've almost distributed all my electrons. Moving on. Okay, finally, I have to make sure now my central atom has an octet, and it didn't before. In the previous page, it just had these 3 bonds, which gave it 6. So I'm going to put 2 electrons, a lone pair on phosphorus. That's my last 2. If I subtract 2 from 2, I've used up all the electrons I had, all the valence electrons that were contributed by these atoms. And now I have given each one an octet, because phosphorus didn't have one. It previously had 6, but with this 2, now it looks like it has 8 electrons as well. So it's stable. The only exceptions to giving an atom, well, I don't know if it's the only ones, but 2 exceptions to giving an atom a complete octet. One is hydrogen, which only gets 2, which I mentioned before. Another is boron. Boron is an exception. It'll have 6, for reasons we're not going to get into here. Sometimes you'll run out of electrons before the central atom has an octet. In that case, you're going to form multiple bonds until everybody has an octet. You'll do that by removing a pair of electrons from each atom so that the octets of the outer atoms maintain an octet. This will become easier when we practice. Okay, so now we're going to practice. We're going to draw the correct Lewis structure for CH2Cl2. Which may be ethyl dichloride, I'm not sure. Organic compounds have different naming, but that's neither here nor there right now. So the first thing we have to do is pick the least electronegative atom. Now again, hydrogen may be the least electronegative, but we never put hydrogen in the middle, because it can only have 2 electrons around it. So carbon is less electronegative than chlorine, so carbon will be our central atom. A tip, usually in formulas, not always, but usually the least electronegative atom is written first. So that will also be a hint to you to put, you usually can put the first atom in the center. At least it'll be a tip as to which one might be the least electronegative. Okay, now we're going to put these other, we have 2 hydrogen, oh wait, I skipped a step, oopsies, we have to add up all our electrons, all our valence electrons. So let's do that. We have 1 carbon. How many valence electrons does carbon have? Correct. It's in group 14, so it has 4 valence electrons. Its outer shell is S2P2. We have 2 hydrogens. Each hydrogen has 1 valence electron. So 2 hydrogens would give you 2 valence electrons, because each hydrogen has an S1, that's all it has, so 2 of them would give you 2 valence electrons. We have 2 chlorines. Each chlorine has 7 valence electrons. Its outer shell is S2P5. So if I have 2 chlorines, I'm going to have 14 valence electrons. So I'm going to add these up. 4 plus 2 is 6, 6 plus 14, that gives me 20 valence electrons in total. I'm just going to leave that here so I can keep track of when I use them up. Now I'm going to distribute my 2 hydrogens and my 2 chlorines around my atom. So this, we'll do them in blue. I'm going to put H, H, Cl, Cl, and I'm going to connect them with bonds. 1, 2, 3, 4. Okay, so I've drawn 4 bonds. 4 bonds. Each bond has 2 electrons, so that's a total of 8 electrons from 4 bonds. I'm going to subtract. That leaves me with 12. 12 electrons are left. Okay, now I have to distribute my remaining 12 electrons around my outside atoms so that they have an octet. Well, hydrogen doesn't need any more. These 2 make hydrogen happy. It makes hydrogen think it has an S2 outer shell, which is all that hydrogen can handle. So I have to distribute these 12 electrons around chlorine. So let's do that. We'll do it in red. So we'll go 1, 2, oh, let's make them bigger. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. So I've given each chlorine 6 electrons, making each chlorine look like it has 8 electrons, because we'll do it in a different color. I'm going to circle this one. Now see, I have 1, 2, 3, 4, 5, 6, and this bond is 2, so that gives me 7, 8. So chlorine looks like it has 8. This chlorine looks like it has 8. That's good. And I distributed 6 and 6, so I distributed 12, so I'm going to subtract 12. So I have no more electrons left to distribute. So now I can't put any more around the central atom, but let's see if carbon has a complete octet. Well, 1, 2, 3, 4, 5, 6, 7, 8. It does. So carbon has a complete octet. It's stable. Hydrogen only needs 2, so these hydrogens are stable. So this is the Lewis structure for carbon dihydrogen dichloride, or ethyl dichloride. I'm not sure the organic name for this, but this is the correct Lewis structure for this compound. Yay! Okay, so we're going to do this one quickly and then move on to a next set of videos, so this one doesn't get too long. So here we have hydrogen cyanide. CNI is called cyanide. We're going to count our electrons. So hydrogen has 1, because it's in group 1. Carbon has 4. And nitrogen is in group 15, so it has 5 valence electrons. Its outer shell is S2P3, so it has 5. So let's add this up. We have 9. We have 10 valence electrons to distribute. Now we're going to put our least electronegative atom in the middle, which is going to be carbon, because it can't be hydrogen. And carbon is to the left of nitrogen, so it's less electronegative than nitrogen. We're going to put hydrogen and nitrogen around carbon, and we're going to connect them with bonds. So I'll put hydrogen here, I'll put nitrogen here, and I'll put a bond between each of them. So that means I've used up 4 electrons here. 1, 2, 3, 4, so I'm going to subtract 4, leaving me with 6 to distribute. I don't need to put any more around hydrogen. It is stable with these 2. I do need to put some more around nitrogen, so I'm going to take these 6 and put them around nitrogen. Okay, so I have 1, 2, 3, 4, 5, 6. Minus 6, I've used up all electrons. So let's see what we have. Okay, hydrogen is stable. It has 2. Nitrogen appears to have an octet. 1, 2, 3, 4, 5, 6, 7, 8, so it's stable. But look at poor little carbon. It only has 4. It needs to be 8 to be stable. It needs to have 8. So we need to fix something here. This is not going to be stable. But we have no more electrons to give to carbon. So what can we do? This is when we will move electrons to create double bonds. So I'm going to move this pair of electrons here and see what happens. I'm going to redraw this down here because I can't erase in my program. So I'm just going to go like this. I'm going to draw my nitrogen with the green, and I'm going to add this red bond here. So this red extra bond came from moving these electrons here. And we still have 1, 2, 3, 4 electrons here. So 1, 2, 3, 4, those are from here. So nitrogen has 8 still, if I were to redraw these down here, which I'll do in a second. But carbon only has 6. Carbon needs another 2. So I'm also going to move these 2 electrons and put them here. Make a triple bond. I'll keep these 2 electrons here on the other side of nitrogen as a lone pair. So now let's look what we have. Nitrogen still appears to have 8. It has a lone pair here, and it's sharing these 6 electrons, these 3 bonds with carbon. So that makes it feel like it has 6 electrons. So it appears to have 8. And now carbon appears to have 8 because it's sharing 2 with hydrogen and it's sharing 6 with nitrogen. So it's stable as well. So this is the stable Lewis structure for hydrogen cyanide, and it is an example of how you would move electrons to create double bonds or triple bonds in this case, so that each atom appears to have an octet. So we'll do more in the next video.